In this video, I'm going to be going through Year 9 trigonometry, Pythagoras' theorem, Year 9 trigonometry, Year 10 trigonometry. I'm going to talk about 30-60 triangles and 45-degree triangles, and then I'm going to talk about adding vectors, so finding the resultant of vectors. I'm then going to talk about equilibriants, and we'll talk about resultants and then equilibriants. We're going to try and talk about concurrent forces and non-concurrent forces in this video as well. So if you're following through with the textbook, I use the Coplanar textbook. We're going to start at page 47, where we learn about forces. They start with concurrent forces. They do it a little bit different order to the way I'm going to go. But then we're going to go to... We're not going to do the three-force method, which is page 56. We're going to go to page 55. So what was that, 46 to 55, something like that? 47 to 55. Okay. So I've recorded another version of this where I went much more slowly, built up from first principles. Some people might say condescendingly, but in this I used lots of different colors to try and make it as clear as possible. In this recording, though, I'm going to try and go quick. So I'm going to say most people understand what Pythagoras' theorem is by the time they get here, but if you don't, I'm going to say Khan Academy and Maths Online both have excellent resources for you to learn. Let's start with the simplest concept, right? So the simplest concept is if I have a triangle that looks like this, if it's 3, 4, and I need to find out what's this remaining side, how can I do that? Well, if we yeah, excellent. Okay, so if this is, we call this a squared, b squared, and so we call this side A, we call this side B, and we call this side C. We can use this formula here, which is c squared equals a squared plus b squared. Okay, c squared plus a squared plus b squared is the Pythagorean Pythagoras' theorem. Okay, so what that means is if you take the square of this and the square of this, you add those together, they equal that. If you look on YouTube, you can find videos where a wheel that has gaps of this size, well, the water that fills up, or coloured liquid, that fills up these two sides is equal to the amount of water that it takes to fill up that side. So most people are familiar with this concept by the time they get to year 11. This is useful for us to find the hypotenuse, and it's useful for us to find the other sides. So to start off with, the hypotenuse is defined as the side that is opposite the right angle, also the longest side. Yeah, so the hypotenuse is the longest side, it's also the side opposite the right angle. And in this case, the hypotenuse is the letter C. I'm going to use HYP, or height. I'm going to use that as, Flavor Flav would say, don't believe the height, but that's my Public Enemy reference for today. That C squared equals A squared plus B squared. So if we have this example here of a 4-3 triangle, this one's going to equal 3 squared plus 4 squared, right? C squared is going to equal that. So C squared is going to equal 9 plus 16. 9 plus 16 is 25. C squared equals 25, therefore C equals 25, the square root of 25, which is equal to 5. Now this is a pretty commonly used triangle. This is actually used by builders and surveyors, that when they're setting out a house, they will actually set a tape measure, and they will measure out 3 meters, 4 meters, and when they get 5 meters, they will know that their tape is exactly a right angle. Yeah, they'll do this to measure out, and they'll call out and say we're good, and then once they've got that, they know they're at a right angle. Obviously they use theodolites as well, but this is a very common method for finding a right angle triangle. Okay, the reverse also works if we want to find this size. Let's say we didn't know for a second that this was 3. How we can find that out is we could rewrite that and say, well, in this case, if we called this A and this one B, we could say that A squared equals C squared minus B squared. In which case it would be the same thing. We'd say 5 squared plus A squared equals 5 squared plus 4 squared, which equals 25 plus 16. Oh, that's embarrassing. When I do the algebra, if I want to find A, I have to minus both sides by B squared. Yeah, I have to minus both sides. They cross out, and what I get is C minus B. Good catch, everybody. By all means, feel free to let me know when I've done something silly. 25 minus 16 equals 9. So a squared equals 9. Therefore, a equals the square root of 9. Therefore, a equals 3. Okay, we're all good with Pythagoras' theorem? Excellent. We can move on. The next thing we're going to do is we're going to look at two regular triangles. So you might be very familiar with 45-degree triangles and 60-30 degrees triangles. Especially if you bought a set square recently, because your set square will come with a 45 and a 60-30 triangle. Yep. Okay, the reason why they give us that is because these are very commonly used angles in engineering, especially when we're learning engineering. We will typically give you forces that are at 30 or 60. I had a teacher before I went to uni, I did a bridging course. I had a teacher, he was from Colombia, Carlos Ortega, and he was a very good teacher. And he said that when he was a kid, that not everyone had a calculator, so his exams, they always used 30 and 60 triangles, so that way you could give your answer as exact numbers. You didn't need a calculator for it. Let's see how that works. Well, let's start with this one here. So we've got a 30, 60. Yeah, in my earlier slower recording, I used lots of pretty colours to try and make it a bit easier, but for here we're just going to go with that. Now, to get that triangle, here's what I'm going to do instead. I'm going to start off with a triangle that's got 60, 60, 60 degrees. Some of you may have seen this already. Some of you haven't got up to surds yet and you haven't seen it yet. All good either way. What do we call that kind of triangle? Equilateral. Right, the idea is that in the other video I go through details on how the angle sum of the triangle is 180 degrees. You're expected to know that. I talked about how you can prove it with a piece of paper, but for the moment we're just going to move on. What I'm going to do is I'm going to cut this in half, this equilateral triangle. So what's this new angle that I've got now? 30 is exactly right. So now I've got 30, this is 90, so it adds up to 180 still. And if this side here was 100, what's this side now? So if it was originally 100, 100, 100, what's this side now?
50.
50, exactly right. Okay, to make the maths a little bit easier for a second, I'm going to start with a different triangle. We'll come back to you. Okay, so we're going to start off with a triangle that's 2, 2, 2. Still an equilateral triangle. We cut it in half. What have we got now? 2, 1. What's this side here? Using the rule, we'd say c squared equals b squared minus, actually, a squared. B squared equals c squared minus a squared. There we go, I got there eventually. Okay, so what's that going to be equal to? This is c is the hypotenuse, so it's going to be 2 squared is, okay, and 1 squared is, excellent. Okay, so that's going to be 3. B squared equals 3. Therefore b is going to equal the square root of 3. Therefore b is going to equal, what's the square root of 3? 1.73. Okay, now I'm going to do the same thing. Actually, I'm not going to do the same thing because I'm lazy. I'm just going to halve everything. What's half of 2?
1.
Ah, good man. What's half of 1?
0.5.
Even better. I'm going to write it as a half, but yeah, whatever. Okay, what's half of 1.73? 0.866? Ah, you
I said that.
Okay. So, if I told you that this big side of the 30-60 triangle was 100%, what is the small side of the 30-60 triangle? 50%. What's this last side? What's this number as a percentage?
86.6%.
Excellent, exactly right. 86.6%. Excellent. That's exactly what we're looking for. Now, here's the thing. In this subject, you're going to get a lot of diagonals that you need to convert into horizontals and verticals. That's what we're going to be doing. And when you do that, especially if they're at 30 and 60 degrees, Some people are going to use their trigonometry, but me, I'm going to say I just take 86.6%. Now, that's not perfect because there's a little bit of rounding error there. It's not perfectly equal. But this 50%, that is perfectly equal. And for me, I just find that this is a lot faster than doing the trigonometry. I'm also much less likely to make a mistake, right? If I told you that something was, if I get an answer and I look at my answer and I get the answer of 150 down here, and I say the answer is 216, I'm like, no, that's wrong. Why is that wrong? Because it's bigger than the hypotenuse. And if I get the answer of 2, I know that's wrong as well, because it's way too small. Yeah, it's smaller than the smaller side. So this is where, I'm sure you've heard since year 5 that estimation is important. Yeah, this is me saying in year 11, estimation is important. You need to be able to do estimating. And this helps me to do estimating. Even if you're like, nah man, I use my 100 sine 30 every time, my 100 sine 60 every time. That's fine, whatever works for you. But this works for me. And so if you start seeing this 86.6 show up, you're going to say, oh, I know what that is. And we've got a name for this number. I call it the disco number, right? I call it that because I have a friend and he's born in 86 and his name is Disco. Well, it's not, we call him Disco. But you could also, if you were keen, I think that Newton wrote his laws in 1686 or something like that. I'm sure you could find another 86 reference, but for me, I'm going to call it the disco number. So if you see that number and I say, hey, the disco number, you're going to know it's 86.6. When Disco had his kid, I tried to get him to give the kid the middle name 0.866. He didn't. I was very disappointed. Anyway, we've done that one. We're now going to come over here. So if I told you this was 1 and this was 1, what would this be? One squared is 1, plus 1 squared is 1. So they're going to add them together, it's going to be 2. The square root of 2 is 1.41. Now, I don't like to do that. I like instead to have my numbers be 100s. So in that case, I'm going to take this number as 1 divided by root 2. Right, 100 divided by root 2 is probably a better way of writing it, which is equal to, if you get a calculator out, 7.7%. Sorry, 70.7%. Again, you don't have to remember that. I remember it. I like to think of the 707. I imagine the 707 as a plane with 45-degree wings. However it works for you. I don't have a name. I don't have a clever name for this one. But you don't see this one come up nearly as often. But it's pretty good. This one, it's good because you get 2 for 1, because they're the same. Hopefully that makes sense. If it doesn't, maybe try watching the other video where I use more colours and I explain things a little bit more slowly. Okay, so we've covered that. The next thing that we need to know is we need to know trigonometry. What is the fundamental acronym of trigonometry? SOHCAHTOA. Right, my youngest daughter, I taught her how to do trigonometry recently, and she said, why don't they just have the buttons say SOHCAHTOA? And I said, that would be great, except for the fact that these buttons were named well before the acronym, I'm pretty sure. It's worth mentioning, I said in the other video, that sine is actually spelled S-I-N-E, and it refers to a wave that looks like that. And then cosine is exactly half a wave out of sync. I hope that that's drawn properly. And so cosine, it's actually not cos, but it's actually cosine. And then tan is short for tangent. Now, tangent, that's beyond my level of maths explanation. You'll ask a maths teacher where tangent comes from. Okay, sine is equal to the opposite side of a triangle over the hypotenuse. What that means is if I have a triangle here, I know how to find if I know my hypotenuse always is the longest side and the side opposite the angle. Opposite the right angle. The opposite side is this side here. Does that make sense? The opposite side. Okay, so if I want to find the opposite side, I would use this formula. I would say sine theta equals opposite, I'm going to write it out properly. Sine theta equals opposite over hypotenuse. And therefore, to find opposite, what I do is I multiply both sides by hypotenuse, and then I cross those out. So therefore, the opposite equals the hypotenuse multiplied by sine theta. Now we could test that out. In the other video I test that out. It's also worth mentioning that there is another way that this algebraic expression works. Sometimes, very rarely in engineering, you might have to find the diagonal instead. You'll have to find the hypotenuse. And when you need to find the hypotenuse, let's have a look at how that goes. So sine theta equals opposite over hypotenuse. Well, through a trick of algebra, which I'm not going to explain now, the hypotenuse equals the opposite divided by sine theta. They just swap. Now, I will tell you that I did not know that that was the second application of SOHCAHTOA until I was much older than I should. Right, in the other video I go into some level of detail, but you don't care. The point is, I did not know that. And my daughter, right, I did some work with her last week, she made those sorts of mistakes because she was rushing it and she didn't show her working out. Now, you have to choose about how much work you want to show, but it's important that you don't get this wrong. Yeah, because if you get this wrong, you're going to make mistakes and then it's going to carry over through the work. What I really want to point out more than anything is, if you use an estimation, if you think about it and say, does that value make sense? Is the hypotenuse the biggest value? If it's not the biggest value, you've done something wrong. Yeah? If the hypotenuse is smaller than the other side, you've done something wrong. And now, life is a little bit too long, too short to make mistakes all the time, but for the now, I'm just going to say, if you do that, you've done something wrong. Sometimes, on the other hand, you don't want to find the opposite side, you want to find this side. What do you call this side here?
Adjacent.
The adjacent. And the rule for that is, I'm not even going to write cosine theta equals adjacent over hypotenuse. I'm just going to write adjacent equals hypotenuse cos theta. Alright, I'm going to give you that one. Right, like I said, we very rarely have to find the hypotenuse as the unknown. If we do need to find the hypotenuse, we usually have both other sides, in which case we'd use Pythagoras' theorem. Hopefully this is worthwhile. Tangent, I never use that in this aspect. What I do use tangent for, I'm going to write this down as another triangle, is often, if I'm told that I have 3 and I have 4, well, I can find the unknown side by using Pythagoras, which we just did earlier. But then I need to find this angle. How do I find this angle? Well, that's where I use tan. I say that theta equals arctan. In Excel, it's written like this. On your calculator, and my calculator, it's written as tan to the negative 1, right? Or in the inverse tan function. What you'll find is when you type that into the calculator, you get something like 37.6 degrees or something like that. Let's type it in. I wonder if that's enough to get copy struck. Probably not. I mean, maybe eventually. But the algorithm couldn't be that smart. Sorry, what I'm doing is arctan, or the inverse tan button, divided by 3, sorry, and then putting in brackets 3 divided by 4, and it gives me 36, it's close, but not right. 36.8. Took a guess, but I was wrong. Now, some of you who do maths, presumably everyone in the class does maths, they'll say, oh, but sir, don't you have to write it as degrees and minutes? Maybe if you're a nerd in maths, but engineers, we just say decimals are fine. And even better, if you write 37 degrees, if you just round up, I will give that as correct. Right, I can't say that your HSC marker will, but if I was marking your HSC question, I would give that as correct. Now, I don't think I ever can, maybe, who knows. The point is, I would mark that as correct. So that's where I use the tangent function. I use the inverse tangent function. Okay, so that's the trigonometry we need to know. That's Year 9 trigonometry. I mentioned that occasionally, just occasionally, they want you to use the sine rule. Right, Year 10 trigonometry. So let's say I've got this triangle here, and it's not a right angle triangle. I've got 110 degrees, and I've got 30 degrees, and I know that this value here is 10. Yeah? We'll go with 10 meters for the sake of it. How am I going to find this unknown side? Well, I'm going to call this A because it's the littlest one. And I'm going to use this rule called the sine rule. I'm going to say A over sine A equals, in this case it's the big side, so I'm going to use C. I'm going to say C over sine C, which is the same as saying A divided by sine 30 equals 10 divided by sine 110. Okay, so how do I write that? Well, then I'm going to say A equals 10 sine 30 divided by sine 110. Okay, 10 sine 30 equals that, divided by, I should have been able to do that in my head, sine 110 equals 5.3. Okay, that's pretty good. And that's going to work if you have a computer, right? And you know, because Excel, just like a maths teacher, doesn't own a protractor, right? Me, I own a protractor. I'm allowed to just get a pen and a protractor, and I can just draw this triangle. And once I've drawn this triangle, I'm allowed to measure the triangle. It's pretty good. Pretty good. Why would you learn this sine rule when you could just use a protractor and a pen? Or pencil. Ideally use a pencil, right? And some of you are like, I'm not drawing anything. And that's the response I get every year. Very few people like to draw graphical solutions, but sometimes it's very, very, very fast. So I should say consider it. I have marked some HSC questions that can be solved graphically. I would say from the 200, 300 that I looked at, less than 5 use a graphical solution. Very rare that I see people use graphical solutions. But that means you need to know this stuff, right? Which, you know, I guess if you're into that. There's also this other rule, cosine rule, something along those lines. I don't know what it is, right? Anyone?
There's a formula.
I know like half the formula, but I don't.
Great, okay. I think it's something like a squared equals...
Plus b, no,
you know what?
a squared plus b squared plus 2
Okay, the point is that none of us here know this. You know why I don't know it? Because I know the angle sum of a triangle, and if I instead had to find side B, and I'm like, can't do B, because I don't know the angle. Now, I don't know this angle. What's the angle? I can't solve it. Oh, look at this kid! This kid, she knows how to do it. It's 180 minus 110, so that's 70, and then minus 30 is 40. And then you can just use the sine rule again. Sine rule, love it. Now let's say for some reason you need to find the angle instead of the size. Very unlikely, but if you did, I would suggest starting by writing sine A over A equals sine C over C. I would write that. It's going to make your algebra a little bit easier. I always put the unknown on the top as the numerator rather than denominator. But if you don't know what the numerator and denominator is, just tune that out, don't worry. Okay, so we've now done Year 9, we've done Pythagoras' theorem, which you may have learnt in Year 8, Year 9 trigonometry, Year 10 trigonometry. Let's put this stuff to use, right? So what we're going to do is we're going to figure out, well, okay, I've got this, so here's what we're going to do. We're going to have this girl, she's going on a bushwalk, right? And we're going to add some vectors together. So we're going to add some displacements. The first displacement is that she's going to go 2 kilometers north. And then she's going to go west 3 kilometers west. And then she's going to go another 2 kilometers north. How far is she from where she started? Can anyone tell me? 3, 2, 1. Yeah. Okay, so let's have a look. In possession of a protractor. Well, actually, I don't even need a protractor for this because I can draw a right angle just, with a set square. 2, then through across 3, then up 2. I could get a ruler out and then just measure that. Yeah, I could just measure that distance and see how far am I from the finish to the start. Yeah, if I just do finish when I start, I can just get the ruler out and measure it.
Yeah, that is this.
But another way I could do this is I could say, well, what was the total amount of north? The total amount of north was 2 plus 2, yeah? 2 plus 2 is better known as 4, just like Clark Kent, yeah? Okay, and then, how much west do we have? 3. Could anyone tell me what the answer is? I'll give you a clue, the answer is 5, yep. Excellent, okay, so how did I figure that out? I applied which theorem? Pythagoras' theorem, 3, 4, 5 triangle. Yeah, I did 3 squared plus 4 squared, 9 plus 16 is 25, I then took the square root of 25, 5, boom. Right, I also happen to know that it's a perfect ratio, so that helps. Right, it's almost like I chose these numbers on purpose. Okay, so I could say that she's 5 kilometers from the starting point. The thing is, now I might say, what's the angle? Now, if we're surveyors do actually usually measure from north. Surveyors measure from north and go clockwise. Whereas structural engineers, they measure from, and we're mostly going to look at structures for these questions, right? I'll be honest, mostly we look at structures. They measure from 0 degrees and they go up, like that. So in our case, we're going to use this one. What would the angle be? Can anyone tell me? What's this angle? What's our bearing, is what we would say in engineering. We would redraw the triangle like this, and say 3 and 4. And what function would we use? Theta equals tan, the inverse of tan, or arctan. What's our opposite?
Three.
3. And what's our adjacent?
4.
Yeah. And we looked at this just a second ago, was it 37.8 or something like that? 36.8? I think that's what it was, 36.8. Good at calculating, everybody. 36.8. 36.89. We're just going to call it 37. Okay. That is the sort of stuff we do in this subject, right? This is how we add vectors. What's another example we might look at? Well, instead of using that, we typically use force vectors. We're typically going to add force vectors. Like I said, we typically use structures. So let's have a look at a structure that we're going to look at. We've got this one here. It's a truss, right? I'm drawing a Warren truss. And then what we've got here is I've got 100 newtons and it's 30 degrees from the horizontal. Right, that's typically how we draw that, measuring from the horizontal. Okay, I'm going to rub this side out. What is another way that I can represent that? I don't want to deal with diagonals. I can't put diagonals into my spreadsheet. So what I'm going to do instead, I want to replace that force with two forces. I'm going to replace it with the horizontal force and the vertical force. How am I going to replace it? I'm going to replace it like this and this. Okay, can anyone tell me what either of those forces are? Want to get your calculator out perhaps? I'll give you the answers, right, just to show you that I know them. Ready? 50 newtons and 86.6 newtons. Do you see what I did there? What number is this? Aiden? Disco number. Okay, so let's have a look. I had this force, which is 100, and I wanted to break it up into its horizontal and vertical component. What is this component? If I know that this is 30 degrees, I know that the small side is half as big as the long side. Yeah? So if I know the long side is 100, the small side is going to be 50 newtons. This one here, and is it going to be up or down, Max? Up or down? Is this line going up or down? Down. So this one's going to be going down. Is this line going left or right?
Right.
So it's going to be going right. What number is it going to be? How much is... Give me a range. Is 200 acceptable? Is 120 acceptable? We'll go the other way. Is 2 acceptable? Is 35 acceptable? Okay, so we've eliminated that. It has to be between, it has to be bigger than 50 and less than 60. What about 86.6? Because I've memorized that. Well, let's assume you hadn't memorized it. What would you do? You would say, is this side adjacent, or is this adjacent, or is it opposite? Well, that's opposite. Yeah, that's opposite. So adjacent is this one here. So what do we use for adjacent? So, ka, or toa? Let's write it up. So, ka, toa. Okay, if you're struggling with this, maybe watch the full video, right? So is sine theta equals opposite over hypotenuse. Ka is cos theta equals adjacent over hypotenuse. If we're finding the adjacent, in this particular case, for the maths that we're using, it's going to be hypotenuse cos theta, which is 100 cos 30. (100 cos 30 is 86.6. Now, like, it's not like it's a magic thing that I figured out, right? What I know is that sine 30 equals 0.5, cos 30 equals 0.866, and that sine 45 or cos 45 both equal 0.707. It's not like I've done anything magical. I've just memorized. You can type these into the calculator, right? You can just type in sine 30 equals 0.5 every time. Cos 30 equals 0.866 every time. Sine 45 0.707 every time. Doesn't change. Okay. I was hoping this would be the less condescending version of the video. I'm hoping that you can see that it's, I'm trying to be engaging rather than just mean. Okay. So this is pretty common, this sort of thing. At the end, we'll get some amount of left and right, up and horizontal and vertical. We'll have to add them together. We'll add them together using what theorem? Pythagoras' theorem. We'll find the angle. So when we get some sort of answer here, we're going to get some sort of answer that looks like this. We're going to find the angle of that using what function? It starts with a t, or there's a t involved. Sokatoa. So I'll give you tan. What's the button look like? This button. Right? Or in Excel, it will be written as a tan. It will actually put it all in capitals and it'll say a tan. Okay. So that's that. Now, the last thing I want to talk about, there's actually a few things I want to talk about. We'll see how we're doing for time. 15 minutes, we should be okay, I guess. Things we need to talk about. We're going to learn about resultants, about equilibriums. I hope that's spelled right. If it's not, I'm a numbers guy, not a letters guy. Resultants, equilibriums, concurrent forces, and non-concurrent forces. So, page 47 in the book, it talks about concurrent forces and non-concurrent forces. So, a good example of this is if I stand on a chair. Here are a stool, right? I have the force of each of the four legs pushing up the stool, right? And I have my force. None of these are meeting. None of these forces are meeting. Whereas on the other hand, if I have a crane that's lifting up a box, those forces are meeting, aren't they? Even the weight of the box, if you were to draw that the weight of the box is going through the box, but in actual fact, the weight of the box is kind of passing through that same point. So these are all meeting in a location, so that's called concurrent. There's another concept which is coplanar and non-coplanar. So these forces, if you're drawing them on a piece of glass, there'd be two forces there, one force in the middle, and then another two forces. They're not in the same plane of glass, right? They're in 3D space instead of 2D space. This crane, again, it's in 3D space. Luckily for you, we don't care about that, right? Forget about it. In the HSC, forces must be coplanar. They all must exist on a 2D force. So coplanar, I think it's with an A. That's not the world's best O. Coplanar equals 2D forces, right? Non-coplanar is 3D. Now, here's the thing. Coplanar forces would be if I draw them on my whiteboard, my 2D whiteboard. If I drew some of these forces like this, right? If I had we'll get to some examples in a second. Whereas on the other hand, if I had a beam and I had 3 people standing on the beam, and I had the beam pushing up on the sides, these ones here, they all meet in one spot, so they're concurrent. These ones don't meet in one spot, so they're non-concurrent. Now the thing is, they don't need to literally touch the same spot. If you go to page 56, which is beyond what I'm going to test people on, there's something called the 3-force method. And what the 3-force method includes, it shows an example where it shows some person and she's lifting up a log. The log has some weight. The log has a rope tied to it. And then there's some force here that's holding the log up, right? It's not floating, it's not levitating, it's the log is being supported by the ground. That makes sense. There's 3 forces. Does it look like these 3 forces are coplanar? Because they are. These 3 forces all meet. Where do they meet? Well, do we know where any of them meet? We don't really know this angle yet. We don't know that angle. But do we know where these 2 forces meet? Let me go through.